Are there any questions from our discussion on Tuesday about the big O notation, the big omega notation, and the big theta notation? Any questions about how those concepts relate to each other? No questions? Okay. All right, so let's go back to those notes first, and then we'll start to build a little bit more stuff on top of that. Just need to find one Moodle page. There we go. And I think we ended with a discussion of the time complexity of the binary search algorithm. Right? Do you guys remember that? Sort of? Where, if you want to look up one single entry within 8 billion entries, it will only take 33 iterations with binary search. If the number of records double to 16 billion, you only need one more comparison. You guys kind of vaguely remember that? Binary search, time complexity, okay? All right, okay, cool. So what we'll do today is something that I usually do, also in my cisp440 class. When I still teach that class, I would use this example to illustrate the concept or why complexity or time complexity is so important when you are going to select algorithms. Okay, so what we'll do is I'm going to use a spreadsheet for this purpose. And we're going to use Google Sheet, and I'll name this Google Sheet Tech and Pat, okay, which is actually what I use in my other class too. So you should be able to follow this spreadsheet right now. For those of you who want to take a look at this using a Chromebook or even a cell phone. A cell phone can open this on Google Doc. So I'll rename this one as Tag and Pat. Okay. So the scenario is like this. Okay. This is back in year 2001. Okay. When the high-tech industry were dropping like flies. So all the companies are downsizing. They're all letting go of developers and whatnot. Okay. Some of you, I think you guys are still old enough to remember this. Okay, in a few years, I have to change it and go like, okay, this is what your parents had to go through. So anyway, back in those days, the companies are letting go of people. So it's down to me and Pat. And the boss says, whoever comes up with a faster search algorithm is going to win. But my boss had no understanding whatsoever of time complexity. So my boss was trying to use real time to measure, which computer or which developer is better. Is that okay? Okay, so that's the assumption. So we have a boss who is somewhat ignorant of time complexity concepts, and want to use the actual real time using a stopwatch to measure performance of a program, and whoever comes up with a system that is, or a search engine that is more efficient gets to stay with the company. Is that okay? So the first thing we want to establish is Tech is using an older computer. So my computer is an Intel 486 computer. As opposed to Pat. Pat is a newer employee, so he or she, okay, because Pat can be either, is using a latest Intel processor. So we'll go ahead and say this is the Intel some kind of i7 processor, top of the line i7 processor. Okay, so right away we have a problem because my boss is not just is not going to factor in the fact that I have a 486 computer running at 16. How fast do those 486 computers run? I think 33 megahertz or 66 megahertz, something like that. 66, right? They started off with 33 and then they boosted to 66, at the very end of that whole generation. Okay. So what we want to do is to find a kind of rough guesstimate of the performance difference between my computer and Pat's computer. How would you go about doing that without looking up benchmarks and stuff like that? I would use the time, okay? I would look at the time when the 486 computer first came out, and look at the time, and compare it to the current time, which is the latest version of the i7 processor. Okay, so you just look it up and say Intel 486 computer, and Wikipedia probably is the first one that pops up right there. And it probably will give you a time frame. Okay, it's produced all the way to up to 2007. That's kind of surprising. And the clock speed went all the way to 150 megahertz. So I'm going to use 2007 as a date. Okay, so going back to my spreadsheet first. So once again, I got lots and lots of tabs here. Okay. So this is 2007, this is 2017. They're off by 10 years. So based on Moore's law, I can kind of guesstimate the performance difference between these two computers. So how do you use Moore's law to factor that in? What does Moore's law say? It doubles every 18 months. Very good. Okay. So that means if my computer is the single unit, in terms of performance, the performance of Pat's computer is going to look like this. It's going to be a power using 2 as the base, and then I'm raising it to the power of whatever this number is. Okay, so we use parentheses, 2017 minus 2007, and then divide this whole thing by 1.5, because 1.5 years turns out to be 18 months. Is that okay? So this part of the equation tells me how many 18 month periods have passed, and then I'm raising the 2 to the power of that thing. So it's not actually too bad. My computer is only 1/100th of the performance of Pat's computer. 1%, less than 1% of Pat's computer in terms of your actual processing power. Are we doing okay so far with this? So it seems like a pretty unfair match to begin with, okay? Because me being the old-time employee has a disadvantage now because my computer, I never updated my computer. They never bought me a new computer because I kept saying, oh, this computer is fine. I use command line tools. I don't need all those high processing power. So is it going to bite me? Well, we'll find out. So the boss basically says, okay, let's pick something that's easy for him to understand. And he or she, the boss, is going to say, let's use search, okay? Search algorithms as a way for this competition to occur, okay? So I decide to look up Wikipedia and find the best search algorithm there is, okay? And the boss says, and I asked the boss, can we assume the array is already sorted? Whatever I'm searching in, can I assume that's sorted? Boss says, yeah, we can sort it first. Okay. And then I look up all the search algorithms, and I found that binary search is the fastest search algorithm based on the time complexity. So I decided I'm going to use binary search. Now, when you look at the algorithm of binary search, it is a little bit more complex. So when you look up binary search, we're just looking at the algorithm itself. It's not really that bad. I mean, many of you probably have implemented binary search already. And is that search or search tree? Just regular search. Okay. So we're looking for the algorithm. I just want to show you what it looks like. Procedure. It doesn't show the actual pseudocode of binary search. Well, that's okay. You'll find this binary search pseudocode. There we go. We should find one here from Khan Academy. Okay. But that's not really pseudocode. There we go. Okay, so now we have binary search. You can do it either recursively or you can do it iteratively, okay? But either way, it's kind of longish, okay? Because you can compare this to linear search. So when you compare that to linear search algorithm, which is really simple, like 5 lines. And let's see if this one has the actual algorithm here. It does, but it's not in the form that we are usually used to. So we go find another one that's easier to understand. Right there. Okay. So we have linear search that looks like this. Basically, it's a 6-line kind of thing. And then we have binary search, which is what, 15 lines or so. Okay. And there's definitely a little bit more complex logic going on because we have a conditional statement inside the loop, or you have to use recursion to kind of do the repetitive part. So I look at both of these algorithms and go like, well, binary search is a little bit more complex. I have to use more lines of code to do it. But the time complexity is really good. It's log of n, okay? N being the number of items in the array. Okay? So I said, look, I'm gonna pick the binary search. Pat, being super duper overconfident because because the computer is much faster, decided there's no way tech can match the performance of that particular newer computer. So Pat decided to choose the easiest algorithm to implement, which is linear search. Is that okay? So let's go ahead and see what's going to happen in that particular competition, which is going to decide who gets to stay with the company and who's going to pack and have to leave the company. So what we'll do is we're going to use one column to look at n, which is the size of the problem. And then we have one column to look at my computer and figure out how much time it's going to take for my computer to figure out the answer. And then we have another column for Pat's computer, or how much time Pat's computer will need in order to solve the problem. Okay. When the problem size is 1, it's pretty easy because both algorithms will need exactly 1 iteration. Okay, because there's only one thing, so check whether that one thing is the thing that I'm searching for, and we're done. So my computer takes 1 single comparison, and Pat's computer also takes 1 single comparison. But what is different is the amount of time it takes. My computer being only having 1/100th of the performance of Pat's computer, it's going to take a little bit longer, right? So my computer ends up taking 1 times, and then whatever this amount is, that's the amount of time that my computer will take to perform 1 single iteration. Is that making any sense so far? Okay, because even though it's just 1 single comparison, my computer is 1/100th of, in terms of performance, is 100th of the performance of Pat's computer. So it's going to take 100 times longer. Yep.
What exactly does n represent?
N is representing the size of the problem, which is how many elements are in the array.
Okay.
So I go like, well, okay, Pat, you won this round, okay? So let's move on to, and then I requested the boss and go like, can we change the problem size so that we can have a rematch, okay? So we'll increase the size, and for some strange reason, I'm not going to try 2, I'm going to try 3. So with 3, my algorithm will take twice as much time. So it's going to take whatever it took in this case times 2. Why is it times 2? Well, if you look at an array with only 3 elements, like that, right? So with binary search, what happens is the first comparison is in the middle. And then what do? If it doesn't match, then you either rule out everything, including this element and everything to the left, or everything to the right. But regardless of which side you choose, you only have 1 element left to compare, right? But I already know that with only 1 single element, I just need 101 unit of time to finish that search. So that's why I just add 1 to whatever I had before. Is that making any sense? No? Okay, so with 3 elements, the first comparison is against the one in the middle. If it doesn't match, then I will either rule out these 2, or I will rule out those 2. That's the nature of binary search. So what is left is either this one, and I only have 1 more comparison to confirm whether this is what I'm searching for, or I have this one left, and then I also need only one comparison to see if that's what I'm looking for. So that's why with 3 elements in the array, binary search only needs up to 2 comparisons to figure out the answer. Even if what I'm searching for is not in the array, it will come to that conclusion in 2 comparisons. Yep.
So it looks at the middle number and sees like, oh, this is greater than it should be, so it knocks off all
Yep.
the things greater than it.
Yep, exactly. So it's using the ordering of the array to help it eliminate everything to the left or everything to the right, depending on the result of the comparison. Is that okay so far? Now, linear search is a little bit tricky to write down because it depends on whether you want to look at the average case or the worst case. Okay, if you're talking about the worst case, it's going to be n itself because you have to look at every single one in order to figure out it is not there. But if you look at the average case, it's going to be about 1/2 of the number of elements in the array. Is that making any sense? Sorry. Okay. So we'll just take the average. Okay. So the average is really just n itself divided by 2. So at this point, my algorithm will take 203 units of time to solve the problem, and then Pat's algorithm will take an average of 1.5 units of time. And Pat is just laughing because the lead is increasing. Pat's computer is now even faster compared to the previous case, compared to mine in terms of ratio. Because it used to be 101 to 1, and now it's 200 to 1.5. So Pat is going like, there's no way you can catch up. You should stop hacking. And they're like, no, let's move on to the next round. So in the next round, I choose 7 as the size of the problem. Why do you think I choose 7? Well, I choose 7 because I'm lazy. Because it's easy, if it's 7, it's easy to figure out how many comparisons binary search will need. I'm going to keep this part here. Because when the problem size is 7, what do you get? You get 2 halves that are exactly the same as this one, and then plus 1 in the middle. Okay? So do you guys see the trick now? Because now I need 1 additional comparison to compare against this new middle element. And then whatever is left look exactly the same as the problem that I had before.
Okay.
Right?
Yeah.
So that means the amount of time that I need to solve this problem, oops, that was not intentional. There we go. So the amount of time that I need is going to be this number times 3. Is that okay so far? Okay. So there's a closed form to do this. I can either use this way, which is whatever this number is, and then plus this particular number. But I need to put a $ here because if I want to do a copy and paste later on, that's needed. With this one, okay, with Pat's computer, it's really just 7 divided by 2 because it's the average case. So it is the number of elements in the array divided by 2, which in this case is 3.5. And obviously Pat is not being threatened at all, okay? Because the lead, if you just look at the sheer net unit of time that Pat's computer is gaining, okay, the gain is increasing, the gap is increasing, it's not decreasing at all. So they wouldn't have any objection to the next one, okay? So what do you think is going to be the n for the next one? 15, very good. It's 15 because it's going to be 2 of the 7s and then plus 1 additional one in the middle. Okay? So that means there's a closed form to n as well. So the closed form of n is really just whatever is before this times 2 to form the 2 sides, and then plus 1, which is the new middle element. And at this point, I can just copy the cells like this because the formulae of these cells are set up to do it correctly. And you can definitely see that hey, this is going nowhere. Tech seems it looks like tech is going to be fired after all, right? Well, let's keep going for a little bit, okay? Next one. Next one. So when you look at the actual net gain, or the actual difference between the amount of time that my computer takes and Pat's computer, it is still increasing. But when you look at the ratio, it is not increasing anymore. And at some point, Pat is starting to sweat right about now. Because that gain is not increasing anymore. And how many times do you think I have to do this or increase the size of the problem before I start to win? Okay, 4 more times. 4 more times is right, because when you look at this number, yeah. 1, 2, 3. 3 more times. Okay? Because Pat at this point is going to say, but this is not fair. We need a little bit more examples. We're going to keep going a little bit more. Well, once I passed, once my algorithm is surpassing, Pat's computer, there's no way, Pat's computer will return or will, beat my computer again. So if we keep going, the difference is only going to increase. But why is that the case? And then Pat says, well, this is not fair. Tech has a 486 computer. I think, because he's an old timer, we need to handicap it even further. Let's give him a 386 SX computer. Okay, it's not just 386, it's 386 SX. What is the difference between a regular 386 versus the 386 SX?
FX 386 is 186 megahertz.
Okay, that's one. Go ahead. Well, the SX has a CPU. Have FPU. None of them have FPUs. Okay, so we'll get back to the FPU thing if you guys want to know about FPUs. FPU stands for floating point units. Okay, which is all present in all the i7, i5, i3 processors. In fact, all the Core 2s are floating point already. So anyway, so if I use an additional handicap, which is an i386 SX computer, and by the way, SX stands for 16. So internally it's a 32-bit computer, but externally only has a 16-bit data bus. Layout easier and cheaper. And for performance, it's going to drop, because every time you want to grab a 32-bit integer, it will take 2 memory cycles instead of 1. But the clock speed is also halved, because it doesn't make any sense to have a really fast processor core when you cannot really add or subtract or compare numbers that fast, right? Because all the time is being spent getting things into the processor to be processed. So if we want to look that up, okay, we can just look up 386 SX and look at the timeline of this thing. 2007, that doesn't make any sense to me. Well, it's produced, doesn't mean that it's going to be used anymore by 2007. So we probably need to look at, when it was sold, the first date that it was sold. Okay, so the 386 was introduced in October 1985. Probably older than some of you, many of you. Okay? And I can tell you it's not older than me.
I was only like 5 days old.
Sorry?
I was like 5 days old.
5 days old, very good. Okay. So let's pick this one, okay? Now the good thing is we're using a spreadsheet, right? So the nice thing of using a spreadsheet is it's very easy to look at a what-if scenario. So in the what-if scenario is, we downgrade tax computer to a 386 computer, and this is probably the wrong date to use for even the 486, but the 386 now we know it is an 85 kind of thing. So the performance difference is now 2,642 times ish. Okay, well that's just based on Moore's law. The exact number may not be the same. Okay, but it gives us a very good guesstimate of the performance difference. Okay, but I'm personally impressed by this kind of number. Okay, when you pick a processor from 85 and you pick a processor from today, assuming they're about the same price, okay? The one from 85, which is how many years ago? I can't do math quickly. 30,
31 years ago.
31 years ago? Okay, you would know. So, 31 years ago
It'll be 32 years in October.
so the one from today is 2 million, more than 2 million times faster than the one that was 30 years ago. Okay? You will say, well, but everything is going to be better over time. Yes, that is true. So you pick out the top of the line Mustang from 1985, okay, and you pick out the top of the line Mustang today. The one from today is probably faster, but by 2 million times, I don't think so. They don't make tires that can do that, right? In physics, you know that your friction can only be pretty much close to 1 of whatever the vertical force is. Right? And then with certain compounds, you can kind of push it to 1.1 at the most in a Formula One race. So there's no way you can make a Mustang that is 2 million times faster than the one from 85. Okay? 20% faster, I can see. Okay, I can buy that. 30%, I can buy that too. But nothing like 2 million times. Are we doing okay so far with these numbers? Okay. So when you look at the rest of the numbers, then you go like, wow, okay, tech is not winning anymore. The question is, how many times I have to do this before I start to win again? That's the only question, is how many times do we have to do this? Okay, what do you think? So with each row, I am only adding a constant to column B, but column C is doubling every single column. Okay, so just looking at the general, numbers, how many times do you think I have to copy these rows before my column starts to look better again?
Maybe like 7.
So right now, let's look at the ratio, okay? Because the ratio will give us some idea. So we just look at the current ratio between these two. It's about 362. Let's call that 512, okay? So that means 9 times. 9 more rows, and my algorithm will start to win again. So we'll take a look at this. Okay, all right. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. One more. And my computer is faster again. Is that it? Okay. I can't really do the comparison because there are too many digits. Yep, I start to win again. Because when I'm using an older computer, it's just changing the shape of the curve. It's changing the scale of the curve, but not changing the shape of the curve. Okay, it's the shape of the curve that is important. So what we are really looking at here is we are looking at 2 functions. Okay, this is n. N is your usual x-axis. Okay, which is the size of the problem. And I'm going to use a linear scale here. Okay, so n is just a linear scale, and this is measured in time. Okay, this is t measured in seconds or whatever unit you want to use. Using linear search, the line is easy because it is linear, just like that. When you use a faster computer, you can kind of make the curve kind of shallower when you have a faster computer. When you have a slower computer, it's more steep. But you're only changing the scaling, okay? The other curve, which is a log curve, okay, looks like this. So by changing the constant, you're only changing the scaling, but you're not changing the nature of the curve, which means the blue line will always catch up with the red line eventually. Okay, it's just a matter of when. Okay, and this is actually, I would call this pretty impressive. Okay, because because I'm using a computer from 85 now compared to the other one, I only had to add 10 more rows before I started to win again. Now this has a lot of importance when you become a developer for whichever company. Okay, most of the time I would argue that you do not have to come up with new algorithms. A lot of research have already been done. A lot of algorithms have been invented to do all kinds of stuff: search, sort, What else do you use algorithms for? Matching, okay? Matching is a big one because of DNA and stuff like that. Okay, so things that can be used for matching is really important too. So those algorithms are done already, which means your job is to, one, choose an algorithm, and two, if an existing implementation does not exist, then you have to use whatever programming language that you were asked to use to implement the algorithm. Is that okay? Is that making any sense? Okay. So the importance now is to figure out, okay, but which algorithm should I use? Okay, should I use linear search, okay, which has a certain time complexity, so it has an average performance of big O of n, or should I use binary search, which has a, typo, but binary search has a different average performance, which is big O of log n. Okay, let me just go between these two again. Linear search has an average performance of big O of n, and then binary search has an average performance of big O of log of n. Which one is better? Log of n. It's always log of n. Because log of n is growing a lot slower when n is large. The log of n does not grow fast anymore. Okay? If you choose the wrong algorithm, then your program is going to take a lot longer to execute. And I think that is partially why programs run slow, because the developers did not really spend the time to research and find out which one is the best. Yep.
Even if it eventually catches up to linear search,
Mm-hmm.
is there situations where linear search would be better than binary?
If you're dealing with a very small array and you're guaranteed that the array is really small, I can see how caching and DDR memory can favor linear search instead of binary search. Because what happens with DDR and caching with modern processors is when you try to read a single element in an array, it's not really just reading that 3 bytes, 4 bytes, or 8 bytes. It's reading a whole chunk of memory in and caching those at the same time.
Okay.
So if you're not going to use the other 64 bytes or whatever that is grabbing, then you're wasting all those memory cycles. So below a certain point, I can see how linear search can actually be always more efficient compared to binary search, but not for long. I mean, for any realistic problem, binary search is always going to win. Mm-hmm. But that's a good question, because that is what's going to set apart quicksort versus merge sort. Okay, so when you look at sort algorithms, okay, they're really bad sort algorithms like bubble sort, selection sort. There's one more. Insertion sort. So all of those three belong to the n squared type of sort algorithm. So they're really slow. The really bad part is we always teach students how to do those kind of sort algorithms first. So they get a first impression. It's like, ooh, sorting. Wow, binary, not binary, but bubble sort. So the first time, it's kind of like a little bird or a little chicken, right? It's an impression thing. It's like the first sorting algorithm that you encounter, has special meanings in your mind. So when you think about sorting algorithms, you always go like, oh, bubble sort. But bubble sort is extremely bad when it comes to time complexity because it's big O of n squared. But when you look at quicksort and merge sort, they are n times log n. Okay, so let's take a look at those two. So we have quicksort. Quicksort is kind of a quirky one to analyze. Okay, so when you get to a 4-year university, you will understand why quicksort is a very kind of quirky algorithm to deal with when it comes to time complexity analysis. But we can just take it for granted here. We'll just say the average performance is big O of n log n. Okay, and then we look at the other one, which is called merge sort. Okay, merge sort is much older, I think, compared to quicksort. And when you look at the time complexity, the average performance is the same. So both of these sort algorithms have a big O of n log n. Okay? Then which one should we use when they are tied? Right? Well, now it depends on the scenario. It depends on the situation, depends on what you're using it for. Quicksort is really great for arrays. Okay, anything that you can fit entirely in memory, you can use quicksort. Okay, because C has a quicksort function call, so we can use quicksort on just about any type of array. How many people know about that one? Qsort is a subroutine that can take on any type of structure, any type of comparison, because all of those things are passed. And it works in regular C. You don't need to use C++ or abstract methods and all kinds of crazy stuff to do this. C can do it with just pointers and pointers to functions. If you learn C++, you probably did not even know that you can take the address of a function and pass that along as a parameter. But that's the good old way of doing things, okay? But the implementation is not, the big thing here. What about merge sort? When do you use merge sort? Okay, let me give you a picture. Hopefully the picture will give you an idea. Mainframe with tapes. Okay. These are not mainframes. See what's going on? Okay, maybe. There we go. Now we got mainframes with tapes. This is a good one. I like this guy. The straight dope. I wonder why it is in this page. But the image is what we want, so we'll just take a look at the image itself. All right. So this is what old computers used to do. Okay, they don't have hard drives. Hard drives came along at a much later stage. So all the data, all the records, okay, your social security records, your tax records and whatnot, they're all stored on tape. What is one big difference between something that is stored on tape versus something that is stored on disk? Just kind of ask your parents about VHS versus DVD. Huh? The quality, okay, quality is one. Okay, let's say that they can do the same quality. Okay? Rewinding, fast forwarding, indexing, and stuff like that, right? The tape can break if you do a lot of back and forth. If you only go in one direction, they're pretty durable. But if you have to do a lot of seeking, back, forth, they do break pretty quickly. Okay, so imagine that your computer only has enough memory to store 2 records. 2 social security records, 2 student records, okay? 2 records of some kind, okay? But you're in charge of a project, but you have to sort a collection of, let's say, 2 million records. How are you gonna do that? In other words, what you need to sort cannot fit into the memory of the computer, not even close. You're off by like a few orders of magnitude. What are you gonna do? Merge sort. So with merge sort, okay, the cool thing about merge sort is, so let's say this is your mainframe computer, okay? This is your mainframe computer. So you have this original tape, so a tape always has 2 reels because it has, when you move it, it has to be stored on the other side. So let's say this is where the data is coming in. It's not sorted, it's all kind of jumbled up. So what you do with merge sort is you go through the mainframe computer. The mainframe computer only needs to keep track of 2 records at any particular time in memory. And then the algorithm can utilize that to decide, oh, this one needs to go to this tape here as an output. This one needs to go to here, as a different output tape. Okay. This is one split. Okay. The merge, which is why we call this merge sort, is to read these 2 output tapes as input, and then just reverse the direction. And you have to do this, split, merge, a few times. And the number of times that you have to do the split, merge is at the most log 2 of n. Now, log 2 of n doesn't sound very impressive, right? Well, we really should know that it's impressive already. So let's say we're dealing with 2 million records. Okay? And let's also say that these 2 million records was sorted in the wrong order to begin with. Okay, that has got to be the worst case, right? Because you're supposed to sort in an increasing order, but it is presented in a decreasing order. So that has to be the worst possible way that you have to deal with this problem. Is that okay? And I said that you have to take the number of times you have to do the split merge is log 2 of this number. So you're dealing with this pen is going. So let's do this one. So we're dealing with log 2 of 2 million, which doesn't sound like a very small number or a reasonable number. The tape is going to break first. Okay, well, let's check it out. This is 2 to the power of 10, or approximately 2 to the power of 10. This is 2 to the power of 1. So in 21 split merge iterations, you will have those 2 million records sorted. That's not too bad. If you think about it, it's not really too bad. Okay, is it going to be really fast? No, because the tapes are not really inherently a fast mechanism. But it only takes 21 times. Is that okay? So this is why merge sort has a very special place in a large amount of data. Because when the amount of data that you have cannot be stored in memory, or memory is very expensive, merge sort is very inexpensive when it comes to how much RAM it consumes, and yet it still has an n log n time complexity. And a lot of people these days just go for quick sort right away, but merge sort actually has a lot of advantages. Now, there's also one more advantage of merge sort in modern architectures. When you're reading from a tape, do you think these tapes or the algorithm is going to seek all day long, go back and forth all day long? No, it's only going one direction, right? So with the input tape, it's only going to read it in one direction. With the output tapes, it's going to output in one single direction. When you flip the direction, it's the same thing. The 2 tapes that will now act as input will only be read in one single direction. The index only goes in one direction. It's not going to be like quicksort, which is all over the place. When you write it back to this one single tape, it is also going in one single direction. And modern architectures, including the caching mechanism and also DDR technology, favors this type of memory access. If it's sequential, it's good. So that's another reason why merge sort may actually beat quick sort when it is implemented correctly using a new modern architecture. It has to do with what we call locality of how you access memory. Are we doing okay so far with these? So even with the same time complexity, you can still fine tune and decide which one you want to use, because they have different nuances, depending on, are you doing most of these in RAM, or do you have, DDR type of RAM, or do you just have, the older type of RAM which does not give you any advantage? Are we doing okay so far with these things? What happens when somebody decides to use bubble sort because it is nostalgic? It becomes very slow, right? And I really suspect that that's what's going on with some of the application programs, because when your document size goes bigger, the amount of time it takes for certain things to happen is going to increase, not linearly, but something that is super linear. It can be squared, can be a lot worse, okay? And I can personally tell you the experience back in my dissertation days, that's a long time ago. I was writing my dissertation using Microsoft Word 2.0. And my dissertation only had about 65 pages, double spaced. 12-point font, double spaced, about 65 pages, which is not terrible. Okay, if you think about it, 65 pages, double spaced with a lot of equations, It's not too bad. But I can tell you, because I do a lot of, I define labels or numbers for the equations, so later on I can say, refer to equation x, y, and z. So I have a lot of cross-referencing. When my dissertation gets to about 40 or 50 pages or so, it just comes to a grind. It just could not do it anymore. Word would just kind of hang up, just stop responding. And I think it might have something to do with something like this, like somebody decided to use an algorithm that does not scale up well. And that was really frustrating. I upgraded to Word 6.0. Okay, for some reason, 6.0 was the next version of Word after 2.0. But that is not really surprising, is it? Where is Windows 9? Well, we had 7, we had 8, and then we jumped to 9.
Windows 7 is not even 7th. It's not even the 7th Windows either. It's not in the right word. It's like Windows.
There's no Windows 6, right? Yep.
No, I'm saying like Windows 7 should actually be like Windows 8 or Windows 9 or something.
Oh, because you mean the internal code?
No, just the order of the releases.
The order? Windows 7 is really the fixed version of Vista, but they ask you to pay for it anyway. Okay, so are we doing okay so far with algorithms or time complexity of algorithms? So most of the time, you don't have to come up with a new algorithm, but you have to understand what is time complexity, what is the big O notation, so that you can choose the right algorithm to make sure that whatever you're trying to do is efficient. Is that part okay? Okay, excellent. All right, so getting back to the notes. And this is, of course, the wrong class. Be good for the next class. So with this class, we are still over at recursions. Okay, so when we look down here, this is the wrong highlight, but we're dealing with recursion right now. Yep.
Can you explain how you got the 10?
Because 2 to the power of 10 is 1024 or 1024, so that's close enough to 1,000. So for every 3 base 10 digits, it's approximately 10 digits in binary. So that's how you can quickly kind of guesstimate how many bits you need when you're given a certain number in decimal. It's just a little quick trick to do it. All right, so we are pretty much done with this slide, I think. So we have the big O notation, which basically means g of n can be used as an upper bound of f of n, and then we have the omega sign, which means f of n in this case can be used as a lower bound of g of n. But if g of n can be used both as the upper bound and also the lower bound, then we use big theta to basically say that f of n is pretty much the same thing as g of n approximately. Are we okay so far with these concepts? The big O, the big omega, and also the big theta. So it's good to get to the big theta, but sometimes we can't get to the big theta, so the big O is the next best thing to do. And this part has to do with time complexity. And we use binary search tree as an example. So for the most part, these are the things that we have already talked about. So I'll just kind of not talk about this part in class, but you should probably still read it. It mentions merge sort, it mentions quick sort. So basically the same stuff that we have talked about in class. So now the question is, what about the master theorem? So there are 2 links to the master theorem. One links to a Wikipedia page, and the other one links to a page that I wrote. Okay, so but they have exactly the same information. It's just that I don't feel like teaching out of somebody else's wiki page, so I decided to write it on my own. So the master theorem is assuming that you have a recursive algorithm where the time complexity T of n, when you are trying to solve a problem of size n, can be broken down to a times and then t of n divided by b plus f of n. Okay, so let's take a look at these components and figure out, okay, what are we talking about? B is, let's start with B, because B is actually the kind of more important part. So this B is basically when you divide the larger problem, which is of size n, into smaller problems, what is the dividing factor? Okay, and B is deciding the dividing factor. Like binary search, in binary search, B would be 2. Because the smaller problem that you have to solve is approximately half the size of the original problem. Is that okay? A is a scaling factor. So basically it's saying, okay, for each smaller problem, okay, well, how many of these smaller problems do we have to solve? In the binary case, in the binary search case, A is just 1. Because there's only, because B is 2, you're dividing the problem into 2 halves. But only 1 half, you have to only act on 1 half. The other half you can just rule out. Is that okay? So in binary search, A is 1, B is 2. F of n is saying not counting the recursive calls, just looking at the rest of the algorithm itself without the recursive part. How much time would that take as a function of n? That is f of n. What do you think f of n should look like in binary search? Well, let's take a look at binary search again, okay? And then we'll try to figure out what is A, what is B, and what is f of n. So let's go back to the binary search algorithm. And we want to look at the one with the actual code. And we want to look at the recursive definition. So this is the recursive definition. So look at this one here. How do we know that B is 2? Which part of this algorithm is giving you a pretty good clue that we are dealing with B equaling to 2?
Divide by 2.
That's a divide by 2. Okay, that's a very good clue. Because the division by 2, which is here, is for computing the index of quote unquote the middle element. Okay, so when you look at how mid is computed, and then you look at the recursive call. In the recursive call, they either keep the lower bound and then change the upper bound to mid minus 1, or they keep the upper bound as high, but they change the lower bound to mid plus 1. In other words, regardless of which way you go, the size of the problem is approximately halved. Is that making any sense? Okay. So that means we are dealing with a B of 2 because we are dividing the original problem into sub-problems of only 1/2 of the original size. Now what about A? A is basically saying, are we doing the recursive call once? Are we doing the recursive call twice? Or how many times are we doing the recursive call? That is what A is deciding. Now in this case you might say, oh, but here's a binary search recursive call, and here's another one. So you might think that A, or the variable A, is 2, but it's not. Why isn't A 2, but it should be just 1? Because it is a conditional statement. Very good, because this is a multi-branch conditional statement. So you either go for the return, the first one, okay, which is the one that I'm not highlighting right now. So when you look at this conditional statement, depending on the result of the comparison, you either do this recursive call or you do this recursive call, but you do not do it both. And that's why A as a variable in binary search is 1. Are we doing okay so far with that? Not counting the recursive call, how much time it takes to do the rest is what f of n is talking about. Okay, so when you look at the when you look at how the structure here, this f of n here is referring to the overhead of each time you call the subroutine. So let's take a look at binary search and take a look at the overhead. So let's take a look at binary search. What do you think is the overhead? Well, the overhead would be dealing with the passing of the parameters, okay? it would be dealing with the comparisons. It would be dealing with the division by 2, a little bit more comparisons, and also the overhead of returning a particular value. Do these operations, do they depend on the number of items that we're dealing with? No, none of those depend on the size of the array. Not even the passing of the array is because A can be passed by reference. So you're only passing a pointer to the beginning of the entire array. You're not copying the entire array again and again and again on the stack. So none of the operations, quote unquote, the overhead operations, is going to be a function of n, which means it's constant time. Okay, so f of n is a constant time function, which is big O of 1. Is that okay? All right. Are we doing okay so far with that analysis? Okay. So once we know those things, okay, so let's go back to the other tab here. There we go. So we know b is 2, we know a is 1, we know f of n is a constant function, which is big O of 1. So now knowing these things, we can now use the master's theorem and compute the actual time complexity of binary search. Now that is the cool thing about the master theorem, is if you can express the time complexity of a recursive algorithm and break it down to this format with a, b, and f of n, then you can apply the master theorem in order to find out what is the actual time complexity of the algorithm in big O notation. Okay? So that is really cool. So we'll take a look at this part here. So we apply these things here to state why it is, why we have a being 1, b being 2, and f of n being k. Let's ignore merge sort for the time being. So this is the master theorem. The master theorem is summarized by a multi-branch conditional statement. This is a multi-branch conditional statement because it says right here, if there exists a constant c of some kind of value, such that f of n, which is the overhead portion of a recursive call, is big O of n to the power of c, and c is less than log b, using b as a base, of a, then we can conclude that the time complexity of this algorithm is big theta of n to the power of log base b a. Okay, that's a lot of mumbo jumbo, isn't it? So the first thing we want to do is, okay, let's see if binary search falls into this category. Okay? What do you think? So let's find out. Okay, I'm gonna use a mouse pad here, so it will also be recorded. And let me just double check and make sure that the recorder is working. Yep, it is. Okay. All right, so we'll use mousepad and plug in those numbers. Okay, we know for binary search A is 1 because we only pick one side to apply the recursive call. We know B is 2 because we are dividing the original problem into a subproblem that is about 1/2 of the size of the original problem. We know f of n is big O of k, or big O of 1, sorry, big O of 1, which is a constant time type of complexity, because it does not depend on n at all. Okay, regardless of n, it is always going to take the same amount of time as overhead. Okay, so we will check whether we can find a c such that it will satisfy all of these requirements. What do you think? Well, we don't really have to find c, do we? Because we say f of n equals to big O of 1, but we want this to be in the form of big O of n to the power of c. Can we find a c such that n to the power of c is 1? Okay, that's a good find. Okay, c appears to be 0. Okay, so let's check whether c equals to 0 is going to make the rest work. Okay, is 0 less than big log b of a? Nope. It doesn't fit, does it? Okay, because c, okay, this is the question, so I'm going to put a question mark here. is C less than log, and then we use the base of 2, log 2 of 1? But the answer is no, because 0 is not less than 0. Regardless of which base you choose, the log of 1 is 0. Okay, so it doesn't fit this particular criteria. Let's move on then. So moving on, we look at the second conditional statement, and it says right here, this time we have two variables that we have to fill. If there exists a variable c, a value c, and a value k, such that f of n can be expressed as big theta of n to the power of c and then log n to the power of k. That's basically what it means. So log superscript k n is really the same thing as log n to the power of k. And c equals to log b of a. So can we find c and k to satisfy this condition? Okay, let's switch to the mouse pad and see if that works. There we go. Okay, so c doesn't really have we don't have a choice about c. C is going to be 0. What about k? K is 0 as well. Okay, k is also 0. So now is the condition met? In other words, does c equal to log b of a? Come on, you guys, you just looked at it before. Yes, it does. Very good. Okay, so c does equal to log b of a because b is 2, but it doesn't even matter because a is 1. It doesn't matter what the base is. Log blah 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 1 is always 0, but c is 0 as well. Okay, so we just we have a condition match here. So as a conclusion, we know that the time complexity of the binary search algorithm is big theta of n to the power of c and then log n to the power of k plus 1. Okay, that seems really, it doesn't look like log n at all, which is what we want, right? But let's plug in all those numbers and see if it works. Okay, so we have big t of n equals to big theta of n to the power of 0, because c is 0, and then we have log n, the whole thing to the power of 1, because k is 0. K is 0, k plus 1 is 1. Okay, let's see if we can simplify this a little bit. N to the power of 0 is 1. Okay, what about log n to the power of 1? Anything to the power of 1 is itself, and the 1 times can be simplified, so we do get log n back. Yep.
Why don't you use the big computation on the if statement, but you use theta for the else statement?
Oh, you mean the big O here, and then the big theta here? Ooh, that's a good question. I think it really should be big theta over here too. But big O is an upper bound. It's really just an upper bound of the estimate. But I think this one is supposed to be big theta as well. Yep.
How are we supposed to know what the big theta is if we're trying to calculate the big theta? Because it doesn't say f of n equals big theta.
You mean this one here?
Yeah.
This one is based on the analysis of the algorithm. So you do have to perform a certain degree of analysis with this part.
I thought we got big O1 though, so how would we know that what the big theta is when our f of n returns a big O?
If it's big O of 1, then your big theta is 1 as well. Because there's no algorithm that can be smaller than big O of 1. Big O of 1 is a constant time, which means it does not even depend on the size of the problem. So big O of 1 is guaranteeing that it's also a big theta of 1.
What if it wasn't 1 though? How would we know?
You would know because it would show that it's different. Okay, let's pick another algorithm to analyze. Okay, let's take merge sort to analyze. Okay, so to understand merge sort, you can read the source code of merge sort and analyze that, or you can go for a much more pictorial way to analyze. Okay, and we still have the picture here, which is great because we can just look at the picture. So the question is, so there are two questions, okay? Because we want to express t of n as a times t of, and then we have to look at the size of the subproblem, which is n divided by by b, and then the whole thing plus the overhead of each iteration or each recursive call. Is that okay? And there are two ways to look at merge sort. This is one way to look at merge sort, but there's another way to look at merge sort. The other way to look at that merge sort is a recursive way of looking at it. You have one input tape, and then you split it into two smaller tapes using that split process, okay, which is what we have here. But then you do it recursively. You look at this tape here, and you split it again. You look at this tape here, you split it again, until you have tapes only containing one single record. Is that okay? So that's the recursive way of analyzing the merge sort algorithm. So now the question is, how many levels do you have to do the splits until you get down to tapes that only contain a single record? What do you think? A single run, anyway. But yeah, just look at a single record. We are looking at a binary tree of sort, okay? So we are looking at a binary tree where each node divides into two subnodes. And we're counting the number of leaves. That is n. We want that to be exactly n. So the question is, what is the height of the tree? How many times do we have to split until we get down to these leaves where they are singletons? It'll be the log 2 of n. Okay, so the height is the log 2 of n. Is that okay? All right? Okay, so that means we have to apply the split log n of 2 times. And when we do the reverse, which is the merge, we have to do it log 2 of n times as well. Is that okay? So now the question is, what is B? We're given a big, huge tape, okay, with lots of records, let's say 10,000 records. With one single split, what do you think is going to be the size of each subtape, or the tape that is coming out of it? 5,000, half, okay? So that means B is 2, very good. What about A? Do I have one single subtape to deal with, or do I have 2 subtapes to deal with? We got 2 subtapes, so A is 2. Now, what about f of n? How much time does it take to take one input tape and split it into 2 output tapes? Or vice versa, how much time does it take to take 2 input tapes and then merge it into one single output tape? It'll be not log 2, it's just n itself. Because it is proportional, because you have to run the entire tape to split it into 2 halves. Right?
Yeah.
So that means if you have twice amount of the data on the tape, it will take twice amount of the time. So, right? Is that making any sense? So f of n is big O of n itself. It is linear to n. So now given these numbers, we want to figure out, okay, so according to the master theorem, which category does this belong to? That becomes our next question. Okay. So we will take a look at the first one first and see if it fits into this particular description. And the answer is, well, maybe, okay? So we look at, the first criteria and say, okay, we have to find a C such that f of n is big O of n to the power of C. Well, we know it is f of n is big O of n, which means C is 1, okay? So C is 1. Okay, I'm going to just do it on the whiteboard. Okay? So we know C is 1. So now we have to do the second comparison, which is the one after the conjunction. So now we are asking the question, is 1 less than log B of A. Well, log B is 2, and A is 2 as well. C is 1. Is 1 less than 1?
Log 2 of 2.
Hmm?
Log 2 of 2.
Yeah, log 2 of 2 is 1. But now is 1 greater than 1? Nope. So it doesn't meet the first criterion. If it doesn't meet the first criterion, then we have to move on to the second one. And we ask, well, can we meet this requirement? In other words, can we find a C and a K such that that happens? Okay, let's find out. C is 1, we don't really have a choice about that, okay, because that's the only portion that controls, how much n we have in f of n. So C is 1 is already fixed. But we have to figure out what is K also in this case. What is K? In other words, we're looking at f of n. Does it contain any log of n component? No. So that means K is 0. Okay, so K is 0. So now we can look at this and go like, okay, what about C equals to log B of A? C is 1. Log 2 of 2 is 1 as well. So C equals to log B of A is true. So now we have true and true. By choosing C being 1 and K being 0, we have met the criterion of the second branch of the conditional statement.
But the first branch, isn't that going to be n squared?
But we couldn't fit the requirement. In other words, that we could not meet
Not
this
that-
requirement.
Not that one. The
In this
data-
one?
The data into the C log to K n. So if you have K is 0, then then that's going to be, well, the whole thing's going to be 1.
But it all works out.
Log K to the n, but K to the 0 would make it 1. The line above. The original line above.
Say again.
The else statement.
The else
The
statement.
line above what you highlighted.
Okay. What about it?
Well, I was thinking if K was 0, then that log would be 1, and there'd be 2 n's in there, but that's all one statement, which makes that second n become 1. So this is my question.
Okay. Have you resolved your question?
Yeah.
Okay. Yep.
So for our f of n for this one, we got big O back, but it's still saying that f of n has to equal big data. So are we supposed to, for that f of n, calculate the big O and big data?
I think for the first one, it's supposed to be big theta too. Just look at the first one as big theta here as well.
Yeah, but when we did the master theorem, f of n gave us back big O. So are we supposed to then convert that to big data?
Oh, if you have big theta, forget about big O and big omega. Remember what big theta is? How it's defined? It means both upper bound and lower bound. Big O is upper bound, big omega is lower bound. But if you can show that it is big theta, you have just that's the best answer you can ever hope for.
But this one's saying we need big data to calculate it.
Yes, but we can establish that because we know how much time it takes to read one tape and split it into two, and that's exactly linear to the amount of records in the tape. So we know that is big theta of n to begin with.
Maybe I'm just getting big, if you're writing as big O, but then you're using it as big data with the theorem.
You mean here?
Yeah. Maybe I'm just getting caught up on.
Well, it is both, okay, because it is both big O and big omega and also big theta. Because when you can establish it is big omega n, which is a lower bound, and big O of n, which is an upper bound, then we know it is big theta of n.
So the f of n will be in big data to begin with when we do that.
Right, yeah. You have a question?
So if we find just the big O, then can we conclude that the big data are gonna be the same?
Not always, because you can always pick a big O that is over exaggerating. But when you have a big O like this, but the big omega is something else like n or 1, then you cannot conclude with the big theta anymore, because big theta is saying the same function can serve as both the upper bound and the lower bound. So if you know the big theta, forget about big O and big omega, because they become consequences of big theta. Okay. Yep.
Is there any case that the last else if will be used?
I have not found one yet. So merge sort falls into the second category as well. And when you spell out the entire thing, it is big theta of n to the power of 1, which is just n itself, right? And then the log, but k itself is 0, but k plus 1 becomes 1, so it becomes just log of n. So it's n log n, which is exactly what the time complexity is for merge sort. Is that okay? So now I'm going to throw a wrench into this whole thing. Okay? What about linear search? There's no recursive version of linear search, or is there? Okay, so let's take a look at different versions of the linear search algorithm. That particular thing is actually addressed in one of my notes here, making an algorithm fit the master theorem. But instead of just reading out of this slide here, I'm just going to show you the code right here. Okay, linear search is really easy to implement. So let's say we're dealing with this. I'm using C, so I'm not going to use bool. So this is linear search f of and let's say we're searching within an array of integers. So const int a is the array, and n is the number of items in the array, and k is what we are searching for. And this is linear search, assuming the array is not even sorted. So I cannot do any type of quick, smart way of getting out of the loop. Is that okay? So the one way to answer this question is we say found is false to begin with, and then we have another variable to control the indexing through the array, and then we say for I equals to 0. Okay, so we don't need to initialize it here, and we can also do the initialization of found here. Found equals to 0, as long as we haven't found what we are looking for, and I is less than n is the number of elements in the array. We do the following, and then we always increment I, after each iteration is the post operation. And what we really need to do in here is really just to assign found to the value of the expression of a bracket I equals to k. And then we just return found. That's one way to do linear search. Is that okay? I mean, I know you guys know how to do it in some other ways, but this is one way to do it. The key is not, whether I use a while loop, or where I initialize I or found, or whether I even need I as a variable, because you can always search from the end back to the beginning. Then you don't need an extra variable for indexing. Okay, so there are many, many ways to do your tricks and make it look different. But regardless, the time complexity is still the same. It is still linear. Is that okay? Can we analyze this using the master theorem? Is it recursive? It is not recursive. Okay. So we can't really use master theorem to analyze this. So now we have to turn it into some kind of recursive algorithm. Is that making sense? Okay. How would you turn this into a recursive algorithm? How do you write recursive algorithms in the first place? Okay. So for those of you who have written recursive algorithms, what is your trick of writing an algorithm recursively? Well, I have to tell you one thing. I have a slight advantage when it comes to making algorithms recursive, because I am lazy and I like to procrastinate. Okay? It's actually a positive attribute when it comes to writing algorithms recursively, because I naturally will tend to say, what is the trivial case? When do I have to not do a single thing and know the answer right away? Does that make any sense? That's when you stop recursion. So I always try to answer that question first. So the question is, in which condition can you come up with the answer like right away and say, oh, we have the answer. So just to be consistent with the other one, I use a found variable to indicate the actual result. Okay. What do you think? I don't even want to have any comparison with the content of the array, because I can say, if you give me an empty array, I can tell you right away false. Does it make sense? Okay, well that's relatively easy, because I just have to say if n equals to 0 or if not n, okay, either one is fine. If you don't like how this one reads, fine, go ahead and make it like that. They mean exactly the same thing, okay? Okay, that's an easy one. What about the else case then? What if this is not an easy one? What about the else? Well, the else is saying that n does not equal to 0, which means the array is non-empty, okay? So if the array is non-empty, there's always the first element, don't you think? Any array that is not empty always has element 0. Okay, so we'll say, oh, well, in that case, we'll check element 0. So we say if a bracket 0 equals to k, then we'll say found is true. Woohoo. Of course, technically speaking, it is better to say it is not false, because we don't know how true is supposed to be represented, but doesn't matter. That's fine points. Okay. What about this else case here? What if the first element is not what I'm looking for? This is where we do recursion. Yep.
Can you make the array into an array that's one smaller than itself?
Yep.
And then
There you go.
call it again?
Yep. So we just say, well, I just want to do the minimum amount of work. The most I would do is to compare a single element. If it doesn't match, you do it. I'm talking to the guy in the mirror, because it's just me who's gonna do it again, right? Okay. So we just say, oh, we'll just ask the next guy to do it. But then you have to be careful, because you don't want to give the other guy the entire array anymore. So the trick you can do here, especially for those of you who use C and C++, is you can just add 1 to the array, because any array is a pointer, and pointer arithmetic, when you add 1, is not really just adding 1 to the address, it's adding the size of one element to the address, which makes it point to the second element of the entire array. Okay? You also want to change n to n minus 1, because now there's one fewer element in this sub-array. And then k doesn't change, because we're not changing what we're looking for. We're just saying, here is the array. It is just one off from the original array, and it has one fewer element, but we are not changing the value that we are searching for. So this is the recursive version of linear search. But does it fit the master theorem format? It still doesn't fit, because the sub-problem is not a ratio of the original problem. It's not a constant ratio of the original problem. It is just one smaller than the original problem. So it still doesn't fit into the format of the master theorem. So we won't have enough time. You can read it, because the next section talks about the actual solution. So the solution to this is to say, fine, if what I'm looking at is not the answer, I'll split it into two halves, okay? One recursive call deals with the first half, the other recursive call deals with the other half. Then it will fit into this format. Then we can do the analysis of, what is the time complexity of linear search? In other words, I'm forcing an iterative algorithm into the format that can be analyzed by the master theorem. Okay? So we'll continue with this discussion on Tuesday. So remember to read up the solution to this particular one. And otherwise, have a nice weekend, and I'll see you guys next Tuesday.